Okay. All right, so we're going to get started on chapter 16, which is the second PowerPoint that we see here. So we're going to click on chapter 16. And again, this is the second half of module 2. So this will help you with the homework problems that are there, or the application problems that are there that are from chapter 16. And we'll wait for this to come up. Oh, of course. All right, so let me see if I can get this. Go backwards. Okay, just gonna reload my page here. Sorry about this. Learning plan, let's try it one more time. I might have to download it and open it, but I'll give it a chance here. It is not liking it. I don't know why. I'm gonna give it one more chance. 3 strikes and you're out. I think they're out. Oh, here it is. I got it. I did try reloading the page. All right. So here we are. So chapter 16. So chapter 16, what we're interested here in is when we have bodies that are going to start to rotate about a center. So in chapter 12, we were looking at translational motion, straight line motion types of things. And now we're going to be looking at things that are rotating. So, so we're going to be looking at translational in combination with, because there will be some instances where we're looking at translational, but there is going to be rotating as well. So as we look here, we're going to be looking to use the formula as we saw in our last chapter 12, some of the forces in a direction. And we always separate out from X and Y. So it will be some of the forces in either the X or the Y or the Y. And then it's going to be equal to mass times acceleration. So the left-hand side is kind of like, if you would, the external forces that are occurring. And on the right-hand side, we call that the inertial terms that are going on. So the mass that's moving in this case and has an acceleration. When there is something other than 0 as the force that we have, there is going to be an acceleration. So that's the dynamic side of things that we're adding, if you would, to our standard statics problems. Now, the next one that we see here is going to be summing the moments. So if you recall from statics, we summed moments when we had things that were rotating. Now, moments, as we had discussed in statics, were based on things that were rotating about a point that we were looking at. I'll wait until everybody's ready. I do want everybody's attention. Okay. I don't mind if you're, following along on your computer, but sometimes it seems like you might be working on other things. So please be following along with what we're doing here. Thank you. So you'll notice that on the left-hand side is our sum of our moments. So if you recall, a moment is going to be the product of the force and the distance that it's offset from whatever point that we're actually summing around. So in statics, we used it a lot in terms of a beam and trying to find the reactions that were unknown. But here we're going to see it, things that are, again, offset from a point that we're interested in. And we're going to set that equal to, now on the right-hand side, that is called H. And H is considered angular, oh no, wait a second. Let me just get the term because it's angular, no, angular momentum. Sorry, angular momentum. And in that, to calculate angular momentum, we're going to be taking the moment of inertia, which is the mass properties of whatever we're looking at, and we're going to be multiplying it by the angular acceleration, okay? Angular acceleration should sound familiar because we did that when we were in kinematics. So on the next slide here, you'll notice that our angular momentum is expanded out into multiplying moment of inertia, capital I, times the angular acceleration. So even though this looks like a lowercase a, this is actually that alpha a, okay, that is for angular acceleration. In kinematics, we saw lowercase a straight line acceleration, and then alpha, kind of like a little fish-looking Greek symbol, is going to be angular acceleration. And angular acceleration just is going to be when we are rotating about a center, or there's some sort of like an offset from an axis. So if we look at the 3 main equations that we're going to be dealing with our problems here, on this next slide, we have some of the forces in the X is going to be equal to the mass multiplied by acceleration that is in the x direction. Then we can do the same thing with the y direction. Some of the forces in the y direction is going to be equal to mass times acceleration translationally or straight line in the y direction. And then lastly, again, when we have things that are offset from a point that we're interested in or rotating about a center, we're going to do some of the moments is going to be equal to the moment of inertia times the angular acceleration that's occurring. Okay. And so we're going to see more examples of the angular acceleration in our things that we're going to be doing today. So let me just make this a little bit smaller. Free body diagrams. So as we're looking at our free body diagrams, we're going to be kind of using the same things and practicing what we learned previously. So we're going to be having for instance, two free body diagrams. One is going to be related to forces, and the other one's going to be related to the inertia terms that we have. When we're related to forces and the inertia terms, we are going to be setting our convention for each one of these problems. So we know that we've always been using up in the y to the right in the x are positive as far as straight line directions or distances. And then if we rotate counterclockwise, for instance, on a moment, that's also going to be positive. Anything down and to the left or rotating clockwise would then be a negatively directed term. Now, when we look at the inertia side of things, we're going to use that very same convention. So when we're on the right-hand side in this case, and we're looking there, anything that is rotating in a counterclockwise direction will be given a positive term, and then anything that's going in the opposite direction will be negative, and then same thing translationally. You'll notice that on the left-hand side, this is going to be our static side. This is going to be the external forces that are, on the body. And then on the right-hand side, we set that equal to those inertia or those mass terms, if you would. So in this case, we've got, because this is rotating about that center of gravity, in this case, as it's called G, we have the angular momentum, the moment of inertia times the angular acceleration that is then going to be rotating about that center. And again, based on the direction that we decide that it's going to be in, or if it's obvious it's going in that direction, then we give it that positive or negative based on clockwise or counterclockwise. All right. So our first sample problem, I don't mind talking generalities, but I think things make more sense when we start doing an example and using what we've got. So our first example that we're going to be looking at is going to be sample problem 16.1. And you can find this in the book on page 1125, okay? And we'll be kind of following along, but I think this illustration is probably a little bit easier to look at. So it says here, the van has a forward speed of 30 feet per second when the brakes are applied, causing the wheels to stop rotating. It was observed that the van skidded a total of 20 feet, okay, when the brakes were locked. What we want to do is we want to determine the magnitude of the normal reaction and the friction force at each one of the wheels as that van skidded to a stop, okay? So, so what we're going to be doing is we're going to be using some of the things that we learned, some of the equations that we just learned in the slides previous, but then also applying some of the things that we've learned in chapters before. So we are going to even be reaching back to Module 11, as well as, Chapter 11, Module 1, but then also the Chapter 12 stuff that we did last time. So hopefully you have your equation sheets from those previous times that we were together, because we will be kind of revisiting some of those things. If not, then you're going to want to make sure that you keep it there. I have been asking you to do equation sheets because I think it's a great way to organize the information, but also as you're working, you're not having to page through the book and try to figure out what you should be using. So, so what I'm going to do is I'm going to go underneath and we will do this problem together. So this is sample. Oopsie. Problem 16.1. Now, again, before we do anything else, make sure you put your convention in the upper right-hand corner, and that is going to reflect not only the positive horizontal and verticals, but also your moments or your rotations that we're going to be looking at here. okay? So the first thing we're going to do is we're going to draw our free body diagrams. Now, we are going to do on the left-hand side here, we're going to draw if you would, the statics free body diagram equal to then the inertia terms or the mass side of things. So I'm going to draw now a simplified version of, so I'm going to draw about this long, the length of our van, and the front point here is going to be our B, and the back point is going to be our A. That's going to represent the centers of our wheels. So this is going to be A, this is going to be B. And then a little bit towards the back, we're going to notice that we have our center of gravity of our van, G, is located here. And it's going to be 5 feet to the right of A, and then it's 7 feet to the left of B. And then additionally, they tell us that it is 4 feet up from the road, okay? We also know that our van is moving, and it's the original or the initial velocity. It's moving to the right at 30 feet per second, okay? That's right before it slams on the brakes, okay? Now, reaction forces. Okay, so this is a known force that we're given, the center of gravity. Oh, and it tells us, oh, that's right. For this problem, they're not giving us the weight of the van. So our final answer will be in terms of, and we'll put our givens and our finds in just a little bit, but I'm just drawing the diagram right now. So we're going to just identify the weight as W, and then our answers will be in terms of W. So we won't be getting like actual magnitudes in the end, but we will be getting them as a function of the variable W. Now, as we look at the wheels, when these are supporting our van, and I really should have put this above here, there is going to be 2 forces acting. There's going to be a normal force, okay? So we're going to call this NB, and that's going to be at both A and B. Now, when we are showing it in this orientation, this NA and NB are representing the front and the back as a whole. So at the end, the problem asks us to determine what is the normal reactive force on each tire. Once we get our answer, we'll simply divide by 2 in the end to get for the 2 wheels in the back and 2 wheels in the front. But as we're doing the problem, we're just gonna solve for the back and for the front. Does that make sense? Okay. And then additionally, there is a friction force because of the fact that we're going to be locking up and we're skidding. There is friction between the tires and the road. Now, these are going to point in the opposite direction of the velocity. So we're going to call this FA. So it's the friction force at A, and FB, again, opposing the direction of the velocity, the friction force at B. I'm going to put it down below. Okay. So that's everything we need for our statics right now. So you'll notice we have the weight of the van coming down, which was a known, if you would, force, not really a known value, but we know that it's W, and then the reactions that are going on at each one of the tires. We're going to set this equal to, okay, so the left-hand side is like our sum of our forces, type of thing. And on the right-hand side, we're going to do that same line, because it's not going to be quite as long in my case. So I'm going to have my A and my B. Now, we are not putting the reactions or the forces here. What we're going to be interested in is going to be what's happening with the mass and the acceleration. Okay, that's the right-hand side, if you would, of this. So this is still going to be G here, but we're not going to put the force of W. At the center of gravity, we're going to draw a vector that is going to represent the mass times the acceleration. So this is going to be M, and then A, and I'm going to put sub X because this is a horizontally directed acceleration. And also the reason that I'm pointing it to the left is because we are decelerating, because we are slamming on the brakes and we're trying to find out what those normal reactions are during that duration. So the acceleration is actually going opposite the direction of the motion, okay, or the velocity. Okay. Additionally, we just have to put on that this is also 4 feet. Okay. So diagram wise, that's what we've got going on. So I'm going to kind of list down below here. These are going to be my givens, if you would. Okay. We know that since this is a English problem, our gravity is going to be 32.2 feet per second squared. Okay, that's going to be our acceleration of gravity. Our final velocity, because we are slamming on our brakes at 30 feet per second, and then we're going to be coming to a stop in 20 feet, our final velocity is 0. Okay. Our original velocity, as we know, is up here. We can list that again, is going to be 30 feet per second. And then I'm going to call it X. It's the distance that we skid. Okay. That is going to be equal to 20 feet. Okay. So this is skid distance. Okay. So those are our givens. And at top here, we've got our 2 diagrams. Then as far as find, okay, what they want us to find in this problem is they want us to find NA, okay? And I'm going to put in parentheses here each tire. So we're actually going to be figuring out NA in terms of the force on the back, but then at the very end, in terms of each tire, we're going to divide that answer by 2. And then we have NB, okay? Again, each tire. And then we have FA, which is the friction force at A because it's the other reaction. Again, each tire. And then FB, friction force in the front. Okay. And I also want to reiterate that all of these are going to be in terms of W. So we're not going to get an actual number in pounds for each one of these. We're going to have a value in terms of W. So I'm going to put in terms of W. Okay. So first things that we're going to do, we are going to find the acceleration or the rate of deceleration that's occurring based on the information that they give us in the problem. So we are going to use our equation. Now this goes back to chapter 11, or if you would, kind of general physics, because we have, now I'm going back to this is module 1, chapter 11, at the bottom of my page here. This is when acceleration is constant. I know that my final velocity squared is going to be equal to my original velocity squared plus 2a times the distance. So our x here is going to be that distance of the skid. So we're going to have our final velocity squared is going to be equal to our original velocity squared plus 2 times the acceleration times x. Okay, and we identified x as that 20 feet. Okay, so make sure you put your equation in variable form first. And then underneath here, we're going to put in what we know and what we don't know. So we have our final velocity is going to be equal to 0. We know that our original velocity is 30 feet per second, but we're going to square that value. Plus 2 times acceleration. Okay, that's an unknown variable. That's what we're going to solve for in this equation. Times 20 feet. Okay. Now, the important thing here is just to remember that you have to have your units in feet and in seconds, and then we're going to get our right thing. So if you don't trust yourself, put the units in. But like I said, I'm giving you a break in dynamics, but your final answer has to have the correct units in it. So just kind of be sure that you have all consistent units here. So now what we're going to do is we're going to solve for A. All right. And so we'll get 900 here. I'm going to push that 900 to the other side. So it's going to be negative 900. It's going to be equal to 2 times 20 times A. So we know that to be 40, right? So we'll divide both sides by 40. And we're going to get acceleration. I'll just put it down here. Acceleration is going to be equal to a negative 22.5 feet per second squared. Okay. Did you guys get that same number? Okay. Now, this is the acceleration that we're going to use going forward, because during this time frame when we're skidding, that's how much it's decelerating, and it's at a constant rate. Okay, at a constant rate. So when we need our acceleration, for instance, up here in the x direction, that's the value that we're going to use, okay? So now the next step that we're going to do is we are going to do our sum of our forces in our x, some of the forces in the y, so that we can solve for some of these, masses and accelerations and such. So our next step, I don't know if I want to do it. Yeah, I can do it down here. Our step number 2, we're going to use the sum of the forces in the x direction is equal to, this is Newton's second law, mass times the acceleration, okay? Now, this is taking, if you would, the left-hand diagram and setting it equal to the right-hand diagram. So if you would, the statics is equal to the kinetics or the dynamics part, okay? So as we look in the x direction, okay, you'll notice here that we have 2 x-directed forces, the FA and the FB. So we are going to say negative FA because it's pointing to the left minus FB for the sum of the forces in the x direction. So again, consistent with it's going left, our convention says going right is positive. Okay. So those are the only forces in the x direction. So we're going to set that equal to mass times AX. And then in this case, this is a negative 22.5. I really should call this AX. I'm sorry. AX, because that's what we called it up on top. And this is a negative 22.5. Well, again, you don't have to put the units in. That's a bad habit of mine. It's a good habit of mine. All right. So as we look here, so if we kind of write this in, if you would, a final form, we would have negative FA, negative FB, and then we would have a negative 22.5. So I'm going to do that. Negative FA minus FB is equal to negative 22.5 times M. Since we have negatives on both sides, algebraically, we can make these all positive, right? All right. Now what I'm going to do is there are 2 unknowns here, or actually 3 unknowns because we don't know what the mass is, right? So we are simply going to kind of put little cloud around that and maybe revisit it, actually probably revisit it a little bit later. Okay. Now, as long as I'm here and I have a little bit of room on the right-hand side, I think I can squeeze it in. The other equation that I'm going to do is I'm going to look in the y direction. Okay, sum the forces in the y. And I do have forces in the y direction here on the left-hand side. But notice I don't have any accelerations or mass on the right-hand side. So we're simply going to say, okay, this is going to be m times ay. But because there is no acceleration in the y direction, that's going to go to 0. Okay, so we are going to sum our forces in the y direction, but we're going to set them equal to 0 because there is no motion in the y direction. So we're going to have a positive NA, a minus W, and a positive NB. Okay, so we're going to have NA minus W plus NB. And we're going to set that equal to 0. Now, just for sake of, kind of putting the negative over on the other side, I'm simply going to say NA plus NB is equal to W, just moving the W to the other side. And then again, we've got 3 variables here that we can't solve for. So this is going to be another one that we're going to kind of shelve, if you would, for a little bit here. Okay. Now, the third equation that we're going to look at is going to be using the sum of the moments around point A, and then looking at the inertia side of things. So I'm going to go to a new sheet because I'm at the bottom here, but I'm going to start at the top here. And we're going to say sum of the moments, and we're going to do it about point A. It's equal to, that means we're going to be summing around that same point on the other side. And this is going to be equal to our angular momentum. So this is going to be I times alpha. Okay. And then we're going to say plus mass times acceleration. So this is straight line acceleration times the distance to point A that's perpendicular to it. So this is like the perpendicular distance on a moment. So I'll show you how we fill that one in. Okay. Now, as we look at our diagram on the right-hand side, you're going to notice that we do have a mass and acceleration. So we're going to add the little x here because that's going to be the acceleration in the x direction that we have. But we don't have the van rotating, right? The van's not rotating. So it does not have angular acceleration. So that's going to go to 0. Okay. Now, this is kind of a new equation to us. So this is looking at the angular momentum, but then we add on the straight line here. So if you wanted to, on your equation shape, I'll kind of show you what I have. I have the mass, or I'm sorry, some of the moments around a point, so that could be G or whatever, would be the I times the alpha, zoom in here a little bit, plus m times the acceleration times the perpendicular distance. So the first part is the rotational, okay, on the right-hand side. The second part is the translational, right? I is moment of inertia, alpha is angular acceleration, m is mass, a, so these two are different. This is angular acceleration here, which is the, I like to say it's the fish symbol, the Greek symbol. And then the a here, this is lowercase a for straight line acceleration, and then the distance perpendicular, which we'll see in a bit. Okay. So this is one of our new equations. The other two here are a repeat from when we were together for chapter 12. Some of the forces in the x is going to be equal to mass times the acceleration in the x direction, and then some of the forces in the y is the mass times the acceleration in the y direction. Okay. All right. Now, since we're not in this equation, we're not going to be using our moments of inertia. We'll talk about moments of inertia on the second two problems. So we'll kind of keep this simple. All right. So now as we look at the right-hand side here, we have mass and we have that acceleration in the x direction. And then the perpendicular distance from, if we're summing around point A here on the left-hand side, we're going to sum around point A here as well. So the perpendicular distance is going to be the 4 feet. Okay. So let's fill in our values. So I'm going to start on the left-hand side here. I'm going to put my finger on A. If you remember this when you took statics, if you took it with me, we're not going to include the forces that are going through A here because they're going through there. There's not going to be an offset distance. So moments are force times distance. So the first offset force is going to be our weight or our W. So we are going to have W times its perpendicular distance, which is 5 feet. And remember, we put that product in parentheses, and then we give the parentheses or that product the direction of the moment. So that means if this is going to rotate, if I put my finger on A and I rotate in the direction of that force, it's going to be a negatively directed moment because it's a clockwise rotation. As I go over to point B here, point B has FB. If I push on FB, it's going to push right through my point. It is not going to cause a rotation, so that's not included, but NB will cause rotation. So my second moment here is going to be NB, which is the force, times the perpendicular distance from A is going to be 5 plus 7 feet. So it's going to be times 12 feet. And the direction of rotation is going to be counterclockwise. So it's a positive out front. Okay. Then we're going to say equal to, we're going to go to the other side of the equation. I and alpha are 0, so we don't have to worry about that. But now we're going to put M for mass. Okay, we don't know what the mass is. But we do know that our acceleration is a negative 22.5. Make sure you put the negative in there because, again, it's a deceleration. And then we're going to have 4 for our distance. Now, remember, this is the product, M times A times our perpendicular distance. We have to go up to the top here, and we have to rotate in the direction of the mass times the AX, and that is going to rotate counterclockwise, right? So that can be a positive out front here. Okay. So questions so far? All right, so now we're simply going to add and subtract things here. So I've got a negative 5W plus 12NB is equal to, this would be a negative 22.5. Actually, let me multiply that out. 22.5 times 4, 90, thank you. So 90 times M. All right, so our unknown variables here are W, N, B, and M. So now all I'm going to do right now is I'm just going to solve for NB because I know that that's something I'm going to have to solve for later on. So I'm just going to solve for ND or NB, sorry. So NB is going to be equal to, I'm going to move my 5W to the other side. So this is going to be negative 90M plus 5W. Okay. And then I'm going to divide by 12 for each one of these. So this is going to be NB. It's going to be equal to negative 7.5 times mass plus 0.4167 W. So that's taking 5 divided by 12. Now, as I said earlier, we're going to be solving these values in terms of W, okay? So right now we've got NB, but there's an M in there, all right? Now this is mass, so we know that, and I'm going to put this over on the side here, we know that mass is equal to weight divided by gravity, right? Weight divided by gravity. So we can say that mass is equal to weight divided by 32.2 because that's our rate of gravity in the English system. So instead of putting M here, okay, we're going to substitute in that W divided by 32, okay? So that means I'm going to have NB is going to be equal to negative 7.5 times W over 32.2 plus 0.4167 W. Oh, and then we have to put a negative in front of the 32. I forgot that, sorry, because it's going down. So this is going to be negative. And since we're dividing a negative by a negative, that becomes positive. Okay. So now we are going to just divide those. So that's going to be NB is going to be equal to 0.2329 W plus 0.4167 W. And now we can add these two together. So our NB is going to be 0.65 W. And we're going to put a cloud around this. Now remember, when we solve for NB right now, this is looking at that front force as a whole. There are two tires there, so it wants to know what it is on each tire. But when we do our final answer, we'll do a division by 2. So far, any questions? Okay, so we've got one of them, if you would, almost done. But we've got NB in terms of W or in terms of the weight. Now, if we go back to our previous equation here, we've got these two other equations with those same two unknowns, but right here, we've got NA plus NB is equal to W. So now that we know what W is in terms of what NB is in terms of W, we can substitute that value that we just got in here to solve for NA in terms of W. So this is going to be NA plus, now instead of NB, we're going to put 0.65 W is equal to W. So now solving for NA, we're going to move this to the other side. So this is going to be W minus 0.65 W. So NA is equal to 0.35 W. And again, that's the back half, if you would, of the back of the van. We'll divide by 2 in just a little bit, and then we'll have our final answer, but we're going to just kind of let this hang out here. The two other things that we need to solve for, so we're almost done with A, we're almost done with B, but the other two are going to be these two friction forces that we have, okay? The two friction forces. So we know that we summed our forces in the x direction, and we got this equation. So using this equation, we are going to find our friction force. So I'm just going to rewrite that equation here. So I've got a start. So this is going to be the FA plus FB. It's going to be equal to our 22.5 times mass. And remember, we already changed these values. This is like a new section. We already changed these values to be positive because they were all negative in the previous sum of the forces. Now, recall from physics or from a previous, we had friction when we were in statics. But if you recall, friction force is always going to be equal to the value of the static or the value of the friction coefficient times the normal force, okay? Now, the normal force is going to be perpendicular to the surface it's riding on. It'll always be 90 degrees to that friction force. So if we go back over here, the friction force at B is going to be equal to the coefficient of friction times the normal force at B. Okay, they're 90 degrees to each other. The friction force at A is going to be equal to that coefficient of friction times NA. Now, when we have the tires, rubber, with concrete, there's going to be a coefficient of friction there. Now, we weren't given it in this problem, but we are going to be able to calculate it because we know how long or how far it took us to go, okay? So we can calculate that friction force or that friction coefficient. And this is going to be what we call the kinetic friction coefficient. There are two values for friction coefficient. There's the static coefficient we talked about in statics. That's when we're not moving. But in this case, we're moving, even though we're decelerating, we are moving. So it's a kinetic version of, okay? There's two different values, even though it's the same materials. They're not off by very much, but they are different. So we're going to call it kinetic coefficient. So for each one of these, we're going to substitute our value for the friction force. So that means we're going to have the kinetic coefficient times NA, okay? And that's going to be FA plus the kinetic coefficient times NB, which is the normal force at B. It's going to be equal to 22.5 times M, okay? Now, just above here, we found out what NB was equal to. So what were NB and NA? So what we're going to do is we're going to substitute where we see NB, we're going to put 0.65 W in here, okay? And the same thing for NA, okay? So we're going to say coefficient of friction here times, oh wait, there's an easier way. We're going to actually factor out the coefficient of kinetic friction. Let's do this instead. And we're going to say NA plus NB. Actually, a little bit of a shortcut. And we know that's going to be equal to 22.5 times the mass. Now, you could do it the other way that I said, but because go back a step here, when we did our sum of our forces in the Y, we had NA plus NB was equal to W. Now we have NA plus NB, we can put W right in there. So we can do coefficient of kinetic friction times W is equal to 22.5 times mass. Now above, we said, oh yeah, mass is equal to W divided by gravity, right? So we're going to take and we're going to substitute that value and we're going to put it here. So in this case, we're going to have coefficient of kinetic friction times W, 22.5 times W divided by 32.2. Now, because we're not doing a moment equation, we're not going to put the negative in here because it's not going to cause a negatively directed moment. Does that make sense? Okay, so it's just finding and using that to find or substitute in for the mass. So no negative in this case because we're just using it for a substitution there, not as a rotation about a point like it was up on top. So now we will do the division of 22.5 divided by 32.2, and we're going to get coefficient of kinetic friction times W is equal to, what's here, 0.6988 times W, right? And now you'll notice that we have W on both sides of the equal sign. They cancel out, right? So our coefficient of kinetic friction is 0.6988, okay? All right. So now we can use that to solve for the friction force in terms of W, for the friction force for A, the friction force for B. So I'm going to have to go to my next page here, and I can say that FA is equal to the kinetic friction coefficient times NA. So we know the coefficient of friction to be 0.6988. And then we also know that NA is equal to 0.35 W, right? So multiplying those two out, our friction force at A is going to be equal to 0.2446 W. So again, in terms of W, this is where we're going to end it. So if we would know what the weight of our van was, we could plug that in and get a number, okay? But we don't. So we have to leave this in terms of W. So we're going to put a little cloud around this one, okay? And then we're going to find FB the very same way. So the kinetic coefficient times NB, the normal force at B, we know that to be 0.6988 times our NB was 0.65 W. And so our FB will be 0.4544 W. So recall that what we're looking for here in our finds, NA, NB, FA, FB on each tire. So the values that we have right now are just front and back. So we need to divide each one of these by 2 to get the final answer that they're looking for. So that's what we're going to do next. So as a final answer, we're simply going to take NA. How can I write that? NA. I'm just going to equal. No, it's not NA. NA is the back. So how should we do this? NA T for tire. There we go. Yeah, good choice. NAT is going to be equal to 1/2 times NA, right? So we know that to be 0.5 times our NA was 0.35 W. So our NA on each tire is going to be equal to 0.175 W. And now this is a final answer for the back, each one of the back tires. Then we'll do that same thing for NB. 1/2 NB is equal to 0.5 times NB was 0.65 W. So our NB, each one of our tires is going to be 0.325 W. And then we're going to do that for each of the Fs. FAT is going to be 1/2 times 0.2446 W. FAT 0.122 W. And then FAB 1/2 times, that was up here, 0.4544 W. So that's going to be, oh wait, this would be BT. I did that wrong. BT. 0.227W. Okay, so these are the final answers then that they were looking for because they wanted it in terms of each tire. So a lot of kind of substitution in this one, not terribly hard, but you know, recognizing those relationships of mass, weight, gravity, and then also recalling that coefficient of friction. So questions on that problem, starting out with the free body diagram in terms of statics on the left-hand side, equal to on the right-hand side are inertia terms. Then we calculated or solved for the acceleration or the deceleration in the horizontal plane. And then using the sum of the forces in the X and the Y, setting that equal to the mass times the accelerations where it was appropriate. And then using our new one, some of the moments around a specified point is equal to the angular momentum, which is going to be the moment of inertia times angular acceleration. Because we weren't rotating here, we could set that equal to 0 for this problem. But then we had to add in the mass times acceleration in the X direction times its distance away from the point that we were going around to you know, see which way it would be rotating. And then that's when we kind of went ahead, solved for the values we needed to in terms of W, some substitution, and then divided our answers by 2 at the end here to get it for each one of our tires. Okay, so that is our first sample problem. I'm going to ask one more time, any questions before we move on? Okay, I am going to stop the recording here to kind of keep this problem separate, and then we'll start a new recording for our next sample problem.